Okay, let's begin by talking about inverse relations by being able to define, like, well, what is a relation? What's a relate in terms of math, and then what is an inverse? Then let's actually, if we're going to be talking about these things, let's define them. Okay. Yeah. So for us, very good. A relation is going to be a sort of a set of ordered pair. And ordered pairs can come in all kinds of shapes and sizes. We can do x's and y's, we can do a's and b's, we can do, all kinds of things, right, for any sort of ordered pairs. Okay, what about the inverse then? What's the inverse represent? When you see the word inverse, the inverse of something, think about, like, okay, if I go out the building and I hang a left and then a right and I end up in a room, and like the bathroom over there, right? So how would I get back to the room, right? If I went out the building, hung a left and a right, I would go out the bathroom and go left and then left, all right? Okay, right and then left, however it is. So an inverse, right? He said, totally said that wrong. So an inverse then sort of gets us back to where we were starting with. So, for example, here's a nice way to represent an inverse. Let's say that I have two sets here, and let's say I have this set is going to represent my domain, so my collection of objects in my domain. And let's say that I have an element in my domain, and that element happens to be the a letter A. Okay, and let's say I have a range over here, and there's one element in my range, and it is B. So then the relation I can talk about is A, B, right? Put in A, get out of B. And I could relate these two by a function f of x. So what this means is that if I take A and I plug it into f of x, I get out B. So f of A would be B in this case. That's what this means, right? So the inverse function then, that means, well, take with what you've been given and go right back where you started with, right? That would be the inverse function, and we denote it as f inverse of x, like this, f inverse of x. That does not say f to the negative 1 power of x, and it does not mean 1 divided by f of x either, right? It says f inverse of x, all right? That's what that means for us. That's one way of thinking about it, and that's the function notation that we're going to be talking about. So if I started with A and I ended up with B, then the inverse would be starting with B and ending up with A. Does that make sense? Okay, cool. Here's another way that we could represent a function. Let's say that I have the function f of x is equal to 3x plus 2. This is a nice linear function, very, very simple, right? So follow along with me then. What would f of 5 be? That would mean 3 times 5 and then plus 2, right? And that would be, well, 15 plus 2, and that would, of course, be 17. So f of 5 is 17. I could represent it as a relation or an ordered pair, 5 comma 17. Let's hear that part? Okay, good. So the 5 was the input, right? What was the output? 17 was the output. Okay, so I started with a function. I gave f of 5. It gave me 17. Let me show you a different function. Okay. I'll call it g of x for now. Okay. So g of x, I'll call this one, is x minus 2 all over 3. Okay. So watch this. So g of 17. If I plug in 17, I would get this. I would get 17 minus 2 all divided by 3. Well, 17 minus 2 is 15. 15 divided by 3. 15 divided by 3 is 5. So I get this relation. I get 17 comma 5. So now the input was 17 and the output was 5, right? So you'll notice here that this is what we say. So f and g are inverse functions of each other. Because, yeah, for the f function, right, gives you plug in a 5, get out a 17. The g function, plug in the 17, get out the 5. So we would reclassify g of x as f inverse of x. I just didn't want to tell you that right off the bat. Okay? Yeah. Here's another example of functions and inverses of functions. Okay. So let's say this is my domain. All right. And in my domain, I'm going to have a couple of elements. I'm going to have 5, 6, 7, and 8. And in my range, I'm going to also have some elements, and I'm going to have the element 9 and the element 10. So how many elements are in my domain for this particular example? There's 4 elements in the domain. How many elements in the range? There's only 2. Right? Okay. So I'm going to do a mapping now. So I'm going to map 5 is going to get mapped to 9. 6 gets mapped to 9. 7 goes to 10, and 8 also goes to 10. So here's the question I have for you. Does this picture represent a function? Yes or no, why or why not? The answer to this is yes. This is a function. And here's the reason why this is a function, okay? For every input in my domain, there is a 1 associated output in the range. So, for example, here we go. If I push the 5 button, what pops out? 9. And I know it for sure. There's no discrepancy, right? If I push the number 6, what number comes out? Also 9, right? It happens to be the same 1, but there's no discrepancy, right? Okay, 7. Push 7, what comes out? 10. Same thing for 8. So yes, this does represent a function, okay? So now, could you draw the inverse, right? If we draw the inverse, what happens? Well, we switch our domain and we switch our range. So here's my domain for the inverse function. The domain is going to have how many elements in it? 2. It's going to have the element 9 and the element 10. The range is going to have how many elements in it? The range will have 4. So I'll have 5, 6, 7, and 8. So if I draw the inverse, I will get this. 9 gets mapped to 5, and 9 gets mapped to 6. So do you see the difference right there? This is not a function. The reason is because when you push, think of it as a vending machine, when you push the number 9, do you get 5 or do you get 6? There is a discrepancy there. So this is not a function, and then likewise we can draw these ones as well, right? So the point I'm trying to make here, guys, is that not every single function and its inverse is also a function, right? It's not always the case that the inverse is always going to be a function, and here's an example of that. So we kind of have to take a look at these things case by case and see. Right now, if it is, then we call it something, and then we'll get to that later on in the lesson. But you guys on board so far? Okay, so I've given you a table of values. These could also be represented as ordered pairs as a relation, right? 0, -1, 2, 0, 3, 2, 4, 3. These can all be ordered pairs, which can be relations. Okay, now what is the inverse is the question for you, so we'll figure it out together. Okay, so what are we going to do? We're going to switch the x and the y, right? So my new set of x's becomes what? -1, 0, 2, and 3. My new set of y's becomes what? 0, 2, 3, and then 4, okay?
Wait, it's called a relation, right?
A relation is a set of ordered pairs.
So it's the one on the left.
No, so like, like this, that, like this right here, right? That's a relation. There's a relation, okay? So, I wanted you to practice drawing the inverse, so, or writing the inverse. So what was the key thing that we did to get the inverse of this? What did we do? One major thing. There you go. We switch the x and the y. We switched them, right? To get the inverse of that function. Okay. Okay, I want you guys to tell me all the points that we just did in the very first one. What were those points that we did?
0, -1.
We had 0, -1, okay.
2, 0.
Hold on a second, let me get there. Yeah, 0, then what?
2, 0.
Then 2, 0, okay, then 2, 0. Good, and then next one was what? 3, 2. Good, the next one was what? 4, 3. Okay, and I'm going to make these all the same color, so I'll make these all red. So you guys good with red? You guys good with red? Okay, good. Here we go. And we'll say done, and then I'll put this away. Okay, so check this out. These are all the points that I've represented in the coordinate plane, right? These are all the ordered pairs that I have right here, right? You guys good with this? And I'll highlight these for you as well. Okay, cool. Now, give me all the points that we did in the inverse function. What were they? -1, 0. Okay, good. Then give me another one. 0, 2. Jake and Jake only. What's the next one? 2, 3. Nick and Nick only. What's the next one? 3, 4. Very good. And let's make these all the same color. So you like purple? I'll go purple. Okay, purple, 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 purple. All right, good. Purple. Good. So we'll say done. We'll hide this. Let's go over here. Let me hit all these for you. Okay. All right. Do you guys notice? I want you to take a look at that. I want you to see if you notice anything about this picture. Talk about it with the person sitting next to you. Okay, so from what I've been told, you guys are telling me that there is this line called y = x, that you're seeing something that it's been reflected over, right? Like that. Is that true? Has it been reflected over that line? Okay, why? But why isn't it like reflected over the line like, x equals 1 or something? Okay, so yeah, I hear a lot of good things going here, right? So if I was going to, the main idea is that we're now switching every x for every single y, okay? So if I want to then take the x-axis, right, as if it's like the real number line, and reflect it over the y-axis, how could I reflect it? Well, I would reflect it over this line of 45 degrees, right? That's how I would reflect two perpendicular lines at 45 degrees. That's why the line y equals x, right, represents the line of symmetry between any function and its inverse, right? So if I have a set of points or ordered pairs, I could easily find their inverse graph just by simply switching x for y and noticing that there is a reflection over that line y equals x. That's an important part. Okay, let's find the inverse. Teach you how to find the inverse using some algebraic tools here. The first thing that we want to do is, since we're going to be switching x's and y's, right, let's take f of x and turn it into the thing we're looking for. So y equals, let's do x squared minus 1. So the first thing I did was I changed f of x into a y. Fair enough? Okay. Then we are switching x for y, every single x for every single y. So therefore x is going to become y squared minus 1. You guys go with that part? Yeah? Alright, good. Okay. So then if I want to resolve this for y, I would get x plus 1 gives me back y squared. Right? But then y then will be equal to plus or the minus the square root of x plus 1. So what did we just find? We found what? What's this thing called? The inverse. So we're going to write it as f inverse of x is now equal to plus or minus the square root of x plus 1. Oh, so there's a process that we just did, right? What did we do? Yeah, so we showed the work. Yes, very, very good. That's true. So change f of x to y. Then what do we do in this next step? Yeah, we switched x for y, right? Then what do we do? Yeah, solve for y, right? You got it. And then the very last step is what? Label it f inverse of x, right? Okay. Awesome. Please take your graphing calculators. Okay. Take out your graphing calculators. I'll take mine out. Looks like this. Nope. Same idea. Okay. So here we go. Let's plug in x squared minus 1. What's that going to look like for us? X squared minus 1. We should all know what that looks like. What's it going to look like, you guys?
X squared minus 1.
Yep. What type of function is that? Yeah, it's a quadratic. Is it facing up or down? It's facing up. Very good. Where's the vertex? Yeah, very good. Very good. All right, let's hit Zoom 6. Here we go. So everybody in the room, we should see our quadratic looks like this. All right. If I want to graph this inverse function, I would put on there the line of symmetry that we just figured out, which would be y equals x. Okay. So it's going to be reflected over this line y equals x, which is my red line that I have there. 502nd square root of an x plus 1. All right, and I hit graph. You'll notice something here. Okay, I only see part of it. Yeah, I have to do the negative as well. So I did this example to show you that the significance of the plus and minus is there to complete the picture, right? So then to graph the full picture, I'd have to actually put the negative, which is the button below the 3, of square root of x and then plus 1. So when I do that, then it would make the whole entire picture kind of give me that magenta color looking thing right there, right? Okay, let's practice this again. Here's f of x equals 2x plus 8. If I want to find the inverse function, what should I do first? Yeah, make that y. So y is going to be, how about 2x plus 8? Then what do I do? So we're going to switch x and y. So x equals 2y plus 8. And then I resolve for y. So x minus 8 equals 2y. We'll divide by 2. So y equals x minus 8 over 2. Therefore, we had just found f inverse of x to be x minus 8 over 2. So here's the original function. There's the inverse. Both are functions across all real numbers there. So these are inverse functions of each other. Yeah. Okay. Let me show you something interesting about your calculators that you might not know. Okay. So go ahead and please clear everything out right now. Just push clear on everything. Okay. And I'm going to punch in these two functions into my calculator. I'm going to do 2x plus 8. So I'm going to go 2x and then plus 8. And then I'm also going to put in there the line of reflection that we just figured out, which is y equals x. And then I'm also going to punch in this function here, which is x minus 8 over 2. So I'm going to do x minus 8 and then divided by 2. And notice that I'm using parentheses for my numerator, so the calculator doesn't think it's x minus 8 then divide 2. Okay? So then if I hit zoom 6, which is the standard window, you'll see, no, there's no negative in this particular case, right? Okay? You should see two lines, right? And they should be reflected over, oh, what happened on that? That looks funky, right? Oh, I'm sorry. The red one is the line y equals x. Sorry. Okay. Okay. Yeah, this doesn't actually look rectangular, right? So your calculator is longer lengthwise than it is widthwise, you know, the way it's straightened up here. So you can change this by going zoom, and then the box in the first one makes your, by hitting enter twice. Oh, not zoom box, excuse me.
Zoom square.
Thank you. Zoom square, which is option number 5. It makes your rectangular coordinate system equal length in x and equal length in y. So it looks more symmetric. So in case you were ever wondering why your calculator was, not looking the way it should, that's the reason why. Okay, we're going to do an example together, the square root of x minus 2. And I would like you to graph this picture in your calculator, the square root of x minus 2. So I'll bring it up. So everybody do that right now. Yep. So I'll go back up to the top, and I'll say the square root we're going to want x minus 2. So everyone please put that in there. And it should look something like this. Alright. And I'm going to actually grab that one. No, just do this. Okay, here with your partner, based on the picture, this is what I'd like you to do. I want you to tell me the domain for f and the range for f, and I'd like you to write it in set notation, please. So the domain and the range based off of the picture that you see right here, okay? All right, Becca, what'd you get for the domain? All real numbers x such that x is greater than or equal to 2. You guys agree with that part? Based off the picture, right? So what is this point right here, right? This point is 2, 0, right? Okay, very good. That point's 2, 0. What's the range? Rachel, what'd you get for the range?
I got all real numbers greater than.
All real numbers y such that y is greater than or equal to 0. And you're absolutely correct. Okay, absolutely correct. Now, everybody, make a sketch next to this equation, just like I have done here on my page. So please make a sketch over there. Okay, here's your task. I want you to draw, like sketch in the inverse based on the picture that you see here. How would it look? What would it look like? Sketch it on your actual paper right next to the one that we have drawn right now. That's your task right now. Okay, I'll give you guys a hint. You guys seem to be struggling a little bit. I'll give you a hint. How does this line, the line y equals x, oops, not 0, sorry, the line y equals x, how does that line play a role in sketching the inverse? We just discovered that this point would be what? It'd be 0, 2, right? Because we'd switch, because this is the x and this is the y. If we switch those, we get 0, 2. So it would look something like this. Okay, now here's your next task. Based on the picture that you see there for the inverse, if this is f of x here, this is f inverse of x there. I've given you the point. Please tell me the domain and the range for the inverse function. That's your task right now. Domain and range for inverse function. Alright, so ladies and gentlemen, based off of the picture, what did you guys come up with for the domain for your inverse function? All real numbers x such that x is greater than or equal to 0. Okay. What's the range, you guys? Okay, please do not say greater than 2. We'll say the whole thing. All real numbers y such that y is greater than or equal to 0. Okay, you guys should be making some kind of an amazing revelation between the domain of your inverse function and the range of your original function. And you should also be making the amazing revelation that the range of your inverse function is the domain of your original function. Do you see that? Why? Because every x and every y is switched. Now, I saw many of you. Let's go ahead and find the inverse function algebraically to this one, okay? And then I'm going to answer your question in a sec. So we had f of x equaled the square root of x plus 2. So then I saw many of you doing this. Y equals the square root of x plus 2. So then x is equal to the square root of y plus 2. So then you got x squared is equal to y plus 2. So therefore y is equal to x squared. Did I do something wrong? Oh, it's the whole thing is minus 2. So I wrote down to begin with minus 2. So change all these. Yikes. See what happens right now. Minus 2. Okay. Minus 2. Yikes. Okay, so finally I get x squared, finally plus 2. Now, therefore, f inverse of x is equal to the x squared plus 2. But when many of you graphed that, you saw a full parabola, right? But you just told me that the domain is only for what? For x values that are only greater than 0. So x is only greater than 0, equal to 0 for this one. That will give you this picture when you graph both of those for only greater than 0. All right, so it's not this picture as well, okay? Because of that domain restriction that we have. All right, so when it is the case that a function and its inverse are both functions themselves, right? Then that's called one-to-one functions, okay? So here's the mathematically precise definition for it. It says this here. If f and f inverse are inverse functions, if they're inverse functions, then here's what this means for us. It's going to look really scary, but it's going to be pretty straightforward once we do it. F inverse of f of x, so the function composition of the inverse with its original function, and vice versa, f of f inverse of x will always give you back the identity x. And this is only true for in the domain.
Yeah, that's true.
Yeah, in the domain of respectively f and f inverse of x. So you have to always consider that. So what does that mean? Yeah, what does that mean? That means that there is for every element in my function, right, it gets mapped to my inverse function, and I can return that element as well. There's nothing that's left out, okay? So as an example, right, let's say this is my domain, and this is my range, right? Every element gets mapped from the domain to the range. That's a one-to-one function. Here's not a one-to-one function, okay? Boom, 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 boom. That one and that one. It's a function, but it's not one-to-one because there's no mapping to get back to this element from the inverse, okay? So that's what that means. That's what one-to-one means for us.
So the one on the left is the only one.
Okay, I'm going to give you a function, and the function I'm going to give you is this. F of x is equal to 1 divided by x minus 1. All right? The domain for this is all real numbers x such that x does not equal 1, because if it did, then I'd have a 0 on the bottom. So I have my domain for my regular function f. I'm going to now do the algebra to find the inverse function f of x. So I'm going to change this to y. That's going to be 1 divided by x minus 1. I'm going to interchange x and y. So therefore, x is now equal to 1 divided by y minus 1. I'm going to resolve this for y. So I'm going to say y minus 1 is now equal to 1 over x. So therefore y is equal to 1 divided by x and then plus 1. Alright, so I have my inverse function, and we got it as 1 over x plus 1. There's all the algebra that supports that. So the domain for this one is all real x such that x is not equal to 0. Okay, so fair enough. So how do I show that this is a one-to-one function? This is what you need to do. We're going to show that f of f inverse of x is equal to x. And here's how we're going to do it. This means f of f inverse of x. Everybody so far so good, right? So that means f, well, what is f inverse of x? It's 1 over x plus 1. Okay, and what do I do with that? I plug it into the f function. So that's going to give me 1 divided by 1 over x plus 1, and then minus 1. Which is just 1 over x, which is just x. That's good. That's what we want to get. We're supposed to get the identity back. I also need to show the other side as well. I have to show this. I have to show f inverse of f of x is also equal to x. So that's what I need to show. So I'm going to do f inverse of 1 over x minus 1. So that's going to be 1 over x minus 1, and then plus 1 on the outside. Well, that's just equal to x minus 1 plus 1, which just gives me back x. So because I have now shown that both, I have shown this. I have shown f inverse of x is equal to x, and I've shown f inverse of f of x is equal to x. That's how I would show that function then becomes one-to-one.